So the next problem we will discuss is this catastrophic forgetting. So let's say that you have some data, input data, as we have in here. We have to classify this data into class 0, class 1. We train our network, and the network somehow finds this boundary between those two data sets. And catastrophic forgetting is when we have already converged to a network, and now we use that network either to train on new data, and the new data has a different distribution from the first one, so the one that we trained on, or we use that network to train on a different task. So here in the slide it is illustrated with a different task. So with a different task, what happens is that the distribution of the data changes. So let's say that it is another classification problem somehow related to the previous one, but now the positive and negative examples, they have different distribution. So the boundaries they change. So ideally what should happen is that somehow the new boundaries are compatible with the old boundaries. So we have here the distribution that we had in the first task, and here the distribution in the second task, and then the boundary between the first task and the second task are compatible, and then the network only has to extend the previous boundary to learn the new task. But that is not what always happens, but what sometimes happens is that the boundary significantly changes. So we can see here that it changes quite a lot, and then it will be forgetting what it learned during task 1 or during the first stage of the training in which we had some data. Here it is illustrated with another example. So let's say that we have two tasks or two data sets that we want to train on. So here we have the error distribution for task A. So this is the minimum for task A, and we have here the error distribution for task B, and then we forget what we learned from task A and move to the minimum of task B. There is a region here which is neither good for none of the tasks, but somehow it is somehow satisfying both. So how to solve this catastrophic forgetting? The first approach could be regularization. So regularization is, okay, we will have a new loss function. So the loss function that we have to train is the new one of the new task, plus something that somehow keeps the network weights similar to what we already found. So let's say that we already found this one. So we have a quadratic loss between our previous weights and the new ones, and this quadratic loss is weighted by this importance of the parameter theta I, importance for the previous tasks. So this can be given from feature information. It is somehow difficult to calculate, but here you have in this paper you have a description how that could be done. This synaptic intelligence is another approach to do the same, only that now the weights are not coming from the feature information, but it is coming from this calculation that somehow is using the current information or the current training to give more or less weight and to give more or less freedom to the weight. Somehow this is encoding the fact that the new laws require to change a parameter quite a lot. So those parameters that want to change, somehow they are constrained by the delta that it is trying to get, and if they are promoted, so they are encouraged by this gradient. So another possible solution is the replay. So experience replay. So you keep examples from the previous tasks, so that while you are updating the network to comply with the new task, you from time to time during the iterations you still put examples from the previous task, so that it is somehow alternating between minimizing the loss for the new task and minimizing the loss for the old tasks through the examples from the previous ones. The problem with that is that you have to keep those examples so that you can replay them. So this is this experience replay, and then generative replay what proposes is to generate the past task example. So you would need another way, maybe a generative neural network or any other means, so that you don't have to keep the examples, but still you have a way to generate examples. The third solution is to change the architecture. So for instance, these progressive neural networks, you freeze the old network, and then the new task will need to be solved by neurons on a different network that somehow utilizes the information coming from the old network that is frozen, and then so the old network somehow computes a latent space that is useful to solve the second task, and then you add these neurons. The fourth solution is to use meta-learning, that is also defined as learning to learn. So this approach is somehow popular, this model agnostic meta-learning. So that is learning multiple tasks simultaneously. So let's say that you have a current configuration of weights. So there is an inner loop. In this inner loop, each task tries somehow to update the weights according to that specific task. However, you don't update yet. The update is coming after considering all the tasks at the same time. The last technique that we will see is this continual learning, that is somehow to add the task to the network. So you are learning all the tasks simultaneously, so you give pairs x, y, and the task that you are solving, and then somehow the network has to configure itself in such a way that the task information is used to minimize the loss functions of the different tasks.